Hi, my name is Ian Van Giesen, and thank you for attending this presentation. Today, I will be discussing on how to ensure the future success of rainwater harvesting systems. So a little bit about me. I'm a mechanical engineering undergraduate student at the University of Georgia. And I had always heard about rainwater harvesting at the university and thought, what about now? What's happened in the 10 years since I knew a lot of these systems had been installed pretty recently at the university. And the more I learned, the more I wanted to understand. I applied for a fellowship for the summer of 2020 to investigate and assess the state of rainwater harvesting systems at the university, to also provide some recommendations as well. I've had the privilege of continuing my work as an intern in the UGA Office of Sustainability, and this is all driven by a passion for sustainable practices and furthering their cause and understanding them better. So I'm really excited to present my content today. So a little bit about what we will be discussing in today's presentation. I will briefly be going through the history of design and integration of the rainwater harvesting systems at the University of Georgia. I will go over the problems and challenges faced in keeping these systems operational and employed. And then I will conclude with recommendations and takeaways for future design and integration of rainwater harvesting systems into a large semi-public institution. So a little bit about the University of Georgia. It's one of the oldest land trust public universities in the nation, founded 1785. We have a population of about 40,000 students and 10,000 faculty and staff. We're home of the Bulldogs. That's the proper spelling you see there, AWG. And apparently UGA was the greatest mascot in college football history, so it is official. A little bit about sustainability at UGA, which has a recent but rich history. In 2007, the Odum School of Ecology became the first standalone academic unit of a research university dedicated to ecology. We have an Office of Sustainability, out of which I work, and they have a couple dozen interns and some permanent staff on hand. So there are also some recent accomplishments of the university, which include phasing out an old coal boiler and replacing it with an electric boiler in 2015, and being gold level star certified, which is kind of like the LEED equivalent except for university. So it's a lot more encompassing and there are a lot more metrics. Rainwater harvesting, the sustainable water metric for the star certification. So UGA has taken sustainability very seriously and has a track record of dedication to these issues. In order to understand how UGA fits into Athens-Clarke County, the county and city in which it is located, it's important to consider the amount of water that the University of Georgia consumes. In 2015, the latest I could get information on the county data, the university consumed 470 million gallons of water. That's about 1.3 million gallons a day. And that is also about 12% of the total county water consumption in 2015. So UGA plays a large role and has a stake in reducing water consumption. In order to better understand why rainwater harvesting even was installed at the University of Georgia, it's important to place it within historical context. So in order to understand what the period of time around when these systems were installed, it's important to consider the effect of drought in Georgia. So droughts are a recurring phenomenon, and while not regular, they do occur, and it's a question of when, not if. So looking at this graph here, you see that in the past 20 years, there have been two very major droughts from 2006 to 2009, and another one from around 2011 to 2013. You can see around 2008 that there's a point in time when over 50% of the area in Georgia was experiencing extremely severe drought. I remember as a kid how this resulted in water scarcity. No one was allowed to water their lawns, and the county government was talking about how to allocate water in this emergency situation. So this is not something this is something that a county and that the university wanted to be more prepared for. So when you look at the installation of these systems and when they occurred in comparison to the droughts, you see a pretty clear trend where the first system was built before the first drought, but it's really in the latter half of the drought from 2006 to 2009, and in the wake of that, most of the rainwater harvesting systems were installed at the university. So you can consider rainwater harvesting as a response to drought, and consider the situation as a cause and effect kind of situation. So considering the kinds of rainwater harvesting systems that were installed at the university, in a span of 7 years, 13 systems were installed. In addition, there were also 75 rain gardens. The rainwater systems came in a diversity of sizes, designs, and end uses. So they were above and below ground tanks and cisterns, outdoor irrigation, and systems supplied water to end uses such as irrigation, toilet flushing, and cooling towers. And there were also several different design approaches from the contractors and suppliers building these systems and designing these systems. Some were more skid-based, meaning that they were located in one centralized location and all the parts were from the same supplier, where others were more component-based, meaning there was a less focused approach and the equipment was spread out. It wasn't centralized. So it's also important to consider when you consider rainwater harvesting, to consider how in a very large institution like the University of Georgia, the way that is situated in an administrative subunit. So thinking about there's all many services, many different operations occurring, and thinking about the specific management division, the way that the different subunits interact with the rainwater harvesting system. Rainwater harvesting systems require the expertise and knowledge of different subunits within the institution. And the way that these different subunits interact within a rainwater harvesting system depends on their specific goals and needs. For example, the grounds department, as its name suggests, is more focused on the way that a rainwater harvesting system is integrated into the irrigation at the university. So if there happens to be a problem, if there's a problem with the irrigation system and it happens to be an extension of a rainwater harvesting system, then the grounds department is going to get involved and start looking at the rainwater harvesting system and looking at and begin to try to understand it better in order to solve that problem. And another example is that the operations and maintenance department, is involved in a way. They're involved by checking on the pumps and making sure that the pumps are in working order. That's their relation to the rainwater harvesting system. So there are a lot of challenges in this kind of decentralized approach to maintain the rainwater harvesting systems, because you have all these different subunits that are focused on specific components or parts of a rainwater harvesting system, which indicates that there is no centralized authority for the rainwater harvesting system and thus no ownership. So one thing, I came into this project, I was a bit surprised to say that I sort of expected seeing that, oh, a rainwater system was broken or it's not working. I'll just come in there to the shop, bring it back, or it's just going to be, oh, it's a clogged filter, clean the filter, replace this leaky union or something like that. But it turned out to be a little bit more complicated, because as time passed, so did the needs and demands of the university changed. So initially, the system was designed for a specific kind of end use, but the university ended up using it for some, the needs and requirements changed for the system. So university no longer had a need for the system. And so this is an interesting dilemma that you have, because the infrastructure is in place, yet the need for the system no longer exists. For example, thinking about irrigation that is specifically for the establishment of plants. And once the plants are established, You don't need the irrigation anymore. So that is something to take note of. Another point to place rainwater systems in some context is the prevalence of combined storm sewer overflows, specifically in our area. These are things, this is an occurrence that happens when the stormwater system is overburdened and begins to spill over into the sewer system, and then that can spill out into the watersheds, which can have a lot of negative impacts on the environment and on public health. So thinking about rainwater harvesting in a way that not only is a water conservation technique, but is also something to help mitigate the occurrence of such negative events as these. And in addition, thinking about rainwater as a part of the affordable water crisis. So I think this graphic speaks for itself, but I was shocked because I had no idea that water was so expensive in a place like Georgia, in Atlanta, versus a place like Las Vegas, whose climate would suggest that water should be more expensive. And I think what this tells is that the cost of water does not reflect its true value in the true scarcity of water, and it's more reflective of the cost of the infrastructure. And so rainwater harvesting, I think, is a part of solving these kinds of problems. So the current state of rainwater harvesting at UGA, there are 17 rainwater harvesting systems, and only 3 are operational and utilized. And I have to qualify and utilized, because just because a system is working doesn't mean it's necessarily being used. So even though all the parts might be in working order and everything's connected the right way, if the switches are off, if it's valved off, it might as well not be working, because the university is not receiving the benefit of having that system. And I'm going to go and get obviously into the weeds in this as I go along. But some of the issues with the systems that were not operational is that there were parts missing and or disabled. So sometimes the water was just turned off to the skid or from the skid or to individual pieces of equipment. And this also included power. Filters were clogged. This included both pre and post filtration systems. So and there was also control systems disconnected, not functioning, which included building management systems not communicating well with other building management systems or relaying the information that they were supposed to. In addition, parts were simply corroded or worn out, and this related specifically to pumps and other in-water equipment. So the way I'm going to go about this is I've chosen 4 out of the 17 systems at the University of Georgia that I think are representative of the kinds of designs out there, the kinds of systems, the kinds of end uses that are incorporated into rainwater harvesting. And I'm going to break down how exactly they work or are supposed to work and the problems and challenges that they are currently facing. So the first project I'd like to discuss is at the Paul D. Coverdell Center for Biomedical and Health Sciences. This facility houses a multidisciplinary mix of research and academic classes and labs. So it also houses the Center for Tropical and Emerging Global Diseases Institute. So I was actually surprised to learn that there are some biologically hazardous experiments that take place in here, including on malaria, leishmaniasis, and toxoplasmosis. So pretty nasty diseases. So water and power, constant supply of water and power is a must at this facility. In addition, there was a rainwater system designed during construction. So the rainwater system collects water from the roof and condensation. It was installed in 2007, and water is collected in an in-cast tank that can hold up to 20,000 gallons. And is cast in place beneath the loading deck. So if you see the picture on the left, beneath the loading deck there. And water supplies 3 end uses: for cooling, toilet flushing, and irrigation. So we have a drawing here showing how the system works, how it's laid out. You see that there is water drawn from the roof and the condensate, and it flows into the underground tank and cistern. The mechanical room is located directly adjacent to the tank in an underground, below-grade mechanical room in the building. There's an intake pipe and 2 external flooded suction pipes that deliver the water from the tank through a step-down filtration system, through a UV reactor to the 3 end uses. The system is in bypass mode, meaning that there is a pressure regulating valve, which means that no external input is needed for city water to bypass the rainwater. Once there is a significant pressure difference downstream versus upstream, the valve automatically opens. There's also a recirculation line in place to keep the UV light cool. I crossed out the irrigation because since design, the irrigation has been capped off as it is no longer needed. Some things to point out in the system here: there's no inlet pre-filter, so everything that's on the roof of this building ends up at the bottom of this tank. The lids to access the tank are extremely heavy. They're about 100 pounds. And for the intake pipe, there's no floating extractor, so it's located near the bottom of the tank. So whatever debris ends up flowing from the tank, from the roof of the building down to the bottom of the tank and happens to land close to that pipe is going to get sucked in and place an extra burden on the post-filtration systems. So that is not a good thing. Some modifications that occurred in the Coverdell in the mechanical room since installation. Originally, there was a chlorine gas injection system, but that was causing intensive oxidation of all the equipment in the room. So if you were to actually go and look at the pipes in the room, everything looks like it's aged 50 years, despite only 10 years having passed. There's also there's a recirculation line installed as the UV bulb was getting pretty hot. And one significant point to take note of is that the system was originally designed to be a makeup system, which means that city water would make up the water inside the tank once it reached a certain low level point. The reason that this system was retrofitted to be a bypass system was in part due to the restrictions a makeup system had on supplying water to the end uses. For example, the system was the sole provider of water to the cooling tower. The cooling tower cannot go without water for more than 2 hours. Otherwise, it will stop functioning as intended for the chilled water system. So it has to always have a constant supply of water. And there had been some problems with some of the pump control, and there have been some problems with maintaining a constant supply of water to the end uses. So the line to the cooling tower was eventually simply bypassed with city water. So at the moment, the system does not supply any water to the cooling tower. In addition, when the system became bypassed, a building management system was integrated into the system to collect data from 3 totalizing flow meters, collecting data on the water flowing to irrigation, to the cooling tower, and to the toilets flushing. However, despite the system being finalized, the communication protocols couldn't communicate with the facility building management system, and there were problems communicating with the contractor that installed the system. So unfortunately, despite having collected data for more than 8 years at this point, the building management system information is not available. So some other problems in the mechanical room of Coverdell. Currently, the bladder tank doesn't hold pressure. And this is important because this helps prevent frequent pump cycling, which can prolong the life of a pump. And the 2 pumps, as you see in that picture, are out of commission. And it's interesting because these 2 pumps are tagged, meaning they are in the system to be in the maintenance schedule system to be checked up on every couple months. by someone from that department. So you can see that it's been checked on for the past 10 years, despite not having worked for at least more than half that time. So just because something the pumps are getting checked on doesn't mean it's working. And it's an interesting dilemma, because this, even if you were to get the pumps working, there's the bladder tank doesn't work, and there's some other components in the system that are not communicating right with each other. So even if you got the pumps to work, you couldn't get the whole system to work. So it's important to think about rainwater, these systems, as a collection of parts that are interdependent on each other. In addition, there are 5 control panels, one of which doesn't do anything anymore, and the other 2 aren't labeled, so don't indicate their function. And as I mentioned before, the building management system used a different platform from the facility building management system. Next, I will be discussing the Special Collections Libraries building. This was also built around the same time. It's a $46 million, at the same time as Coverdell. It's a $46 million project, and there's a focus in the building on archival processes, and it also hosts space for classrooms and galleries. There's a 30,000 square foot high density vault in the basement of feet of archival storage. The library is also built over a natural spring, which is important because the water is also supplied to the same tanks as the rainwater. There is a rainwater system included in this building, installed at the same time that the building was constructed in 2010. And water is collected from the metal roof and the dewatering system and stored in 2 below ground 20,000 gallon corrugated tanks. The original end use for this system was landscape irrigation. So this was for the establishment of new planting and the green lawn in front of the building. However, since then, the plants have established themselves and the irrigation lines have been severely damaged, so there's no longer possibility of using that same irrigation setup. I'm going to go over a drawing of the Special Collections Library rainwater system to give you all an idea of how this is supposed to work. Water you can see coming in from the roof and dewatering system into 2 below ground tanks and cisterns. These tanks and cisterns, these 2 tanks are not connected, so there are 2 separate intake pipes, which are pumped up by single flooded external suction pump. In order to only pump from one tank at a time, there are 2 valve actuators that are controlled by the pump to decide which tank water is to be drawn from. The pump pumps the water through a 100 micron filtration unit and out to a 3-way valve actuator. The system is in bypass mode, meaning when the 3-way valve is open in the right position, city water will bypass the rainwater to go to irrigation. This is controlled by the pump, and this function is controlled by the amount of water in the tank. So some things to take note on the system here. Again, as I mentioned before, there is no inlet pre-filter, so everything ends up in the tank. There's no floating extractor, so whatever this is wherever the water is being pulled from exactly, it could end up into the system, thus placing an additional burden on the filtration system, post-filtration system. Some other problems with the system, since its inception, the pump was operating very loudly. This was indicating that there was possible cavitation. This theory is also supported by the fact that the pump rests at about 15 to 20 feet above the level of the water in the tanks. This is high enough above water for cavitation to start. So cavitation is when a pump pulls so hard on water that it is able to pull the air out of the water. The air bubbles implode on the impeller in the pump, causing damage to the impeller, which can really reduce the life of the pump overall. In addition, there are multiple redundant valves and unions leading from the tanks to the pump. Each of these points is a possible entrance point for additional air to cause additional damage through cavitation. So this is a problem. There's also an unsolved filter backflush system that never worked, and the filter there is very difficult to maintain. It's extremely difficult to unscrew and take off and put back on because of its unwieldy position. It's too close to the back panel there to be really easily maneuvered. Something else to take note of here is that the water from the pump goes in a sort of U shape all around it. And this maybe would be a problem, but for the fact that the pipes above it were leaking. So all this leaking water was leaking directly onto the pump and motor of corrosion. And definitely having water sprayed all over a pump like that is not recommended. A pump is not meant to be in water. Some additional problems with the rainwater harvesting system there is that there's some valves and components on the side of an inner enclosure for the control system that are very difficult to access. You can hardly see the things on that side. So there are some ergonomic problems with the system that have made it very difficult to maintain over time. Some problems that I didn't put into pictures. There's some irrigation wires that feed into the control system for the rainwater harvesting system. And this demonstrates a sort of misunderstanding of what the system was meant to do. The system was not meant to control the irrigation system. It was meant to simply provide pressurized water. In addition, as I mentioned before, there's no pre-filtration on incoming gutters and drains, and only one tank level transducer still functions. The consequence of the last point is that because it indicates that there is no level in one of the two tanks, water is currently only drawn from one tank, and they're relatively expensive to replace. So at the moment, water can only be drawn from one tank. At the moment, the system is turned off, it is valved off, it's no longer being used, and after discussion with the grounds department, it appears that there's no longer a need for the system. So despite the fact that all this money and all this infrastructure is in place, the system is not being used because needs changed over time. So the next system I will be discussing is the horticultural support building. This was installed in 2017, the same time as the construction of the building. It collects water from the metal roof, and the water is stored in 3 below-ground 1,700-gallon corrugated tanks. Water is supplied for 3 end uses, some toilet flushing in the building, a hose bib, and cooling pads in the 3 adjacent greenhouses. So we have here a drawing of the rainwater harvesting system at the support building, and you see that water is collected from the roof, is passed through a in-ground basket filter that goes to 3 underground tanks and cisterns. They're connected. There's a single submersible pump that collects water from the middle tank and pumps it up to the mechanical room in the horticultural support building. It passes through a step-down filtration system, so 50 micron to 5 micron, through a UV reactor, where it then feeds out to 3 end uses. The system, again, is in bypass mode. This time, there is a bypass valve actuator that is controlled by the pump, and the pump on whether or not to open the valve actuator is a level transducer in the tank. So if there is low level in the tank, the valve actuator opens up, allowing city water to bypass the rainwater. The takeaway from this drawing really is that this is a fairly well-designed system. There's not a whole lot wrong with it. It works pretty well, but despite the fact that it works well, doesn't necessarily mean it's been utilized. And so from its installation in 2010, it worked for about it was being used for about 5 to 6 years. And then for several years, it was simply off. And there's no clear reason as to why, but some of the reasons I think maybe that the system was not being used is that there is no on-site documentation. There's no knowledge of the system, the building management people at the botanical gardens where the system is located, and there's a lack of again, ownership and responsibility for a system. So despite the system being something that is, works well, is relatively well designed, it hasn't been used. An additional point I'd like to point out here is that the UV reactor is plugged into an old outlet with a light switch. So if you turn the light switch off and on, unlabeled one, you actually turn on and off the UV light, which is definitely a problem. So the last system I like to point out here is the Founders Garden. So this is one of the older buildings on campus. It was initially a residence hall for professors on campus, built in 1857. It's a living memorial to the 12 founders of the first garden club in Georgia, and it's currently managed by the UGA College of Environment and Design. It's a really beautiful place. There are a lot of interesting garden designs here. And as part of efforts to supply water on-site, to the system, a rainwater harvesting system was installed in 2007. The system collects water from 800 square feet of metal roof from the building, and the water is stored in one above ground 620-gallon tank. It supplies water to one end use, irrigation via a small pump. And that's it. And the reason I point this system out is because it's, and we'll see a drawing right here. You see that there's first flush diversion, there's pre-filtration before the tank, there's a pump plugged into a GFCI outlet, and then it pumps out to a hose bib. And so the system is simple. It's dirt simple, as simple as it gets. And I think the takeaway from this system is that one is better with a simpler system that works and not a complicated one that doesn't work. And so I also find it compelling visually to go, when you look at the system, you really don't have to know too much about rainwater harvesting in order to understand what's going on here. So you can see where the water goes, how the water comes in, how the water leaves, where does it overflow. You see the pump, you see where it's plugged in, and you can see the switch to turn the pump on and off. There's minimal initial know-how required. And that's the reason that since this system was installed, it has consistently worked and been consistently used, which is a very important takeaway. So yes, and this is the only system of that kind that's worked like that in the University of Georgia consistently. So conclusions. So there are a number of problems I have seen and experienced up until this point, and am continuing to see and experience. The first of which is very common, post and pre-filters being clogged, and the first flush diversion units being clogged as well. So these are pieces of equipment that are great to have in a rainwater harvesting system, and it can be considered nearly an essential component of rainwater harvesting. However, if they're not cleaned, if they're no benefit, and if anything, can serve as a source of some problems. So if they're not going to be maintained, it's better to not have them at all. The fact is, they're there in designing some of these systems. They can be a great asset in preventing medium to large size debris from entering the tank. Some other things I've encountered, valves and switches being turned off. This is the reason for it is not always clear. It can be that some people, these systems aren't essential parts of keeping the university operating. So if it turns out to be harder than expected or too complicated, they're just turned off because it's not worth the trouble that they pose. and there have been, as I mentioned before, problems with the control systems. So if the piece of equipment that provides input to the control system is no longer working, then the control system isn't reading the input correctly and then outputs a wrong signal, or perhaps the piece of equipment that it's supposed to output to is not reading the right kind of signal, and then the system is not going to work very well. Or maybe a case that, for example, like this includes building management systems, they are not able to, they don't have the correct kind of communication protocol to communicate with the facilities building management system, or the contractors, suppliers of the building management system have since left, and there's no way to get the information that these systems have been collecting. This is an ergonomic issue. This is frequently related to tank lids being very heavy and sometimes being lost under a couple feet of pine straw. So if these tank lids are extremely hard to open and access, it's going to discourage the maintenance of tanks, which is good practice. If these tanks aren't checked up on at least semi-regularly, there can be problems that crop up for unknown reasons. So, for example, the lids at the Coverdell Center are 100 plus pounds, and the equipment, it's impossible to open up manually. You need a piece of equipment that's not located on site. You have to plan to bring that there. It's a whole lot of hassle. It's a whole lot of trouble, and for that reason, these tanks have not been checked on. And it's difficult to say. It's unlikely that that system has been checked on in any recent period of time. Some other problems, over complexity in design. So the more complex the system is, the less likely it is to work. And so having had conversations with the people who interact with these systems and, have a desire to see them working again. But in the past, when they tried to approach them and tried to fix them, there was a lack of documentation. There was a lack of guidance on what to do, how the system works, and how to maintain the stuff. What requires maintenance? What's the correct position of the valves? If there's no documentation on how it should be, then it's only a matter of time before someone accidentally turns a valve and doesn't really know what their correct position is, and which can lead to further problems. So, and also missing equipment. Again, there's for one of the systems, the pump is just gone, and no one knows where it went. And again, in a large institution like the University of Georgia, if there is not a protocol for the way that these systems need to be maintained and treated and handled, things like this are going to crop up from time to time. So a lack of maintenance is the takeaway, I think, from all these issues, is that there's in terms of, what parts need to be taken care of when and how, and who's going to do it. And a lot of these things are fairly simple. Cleaning the filters is just a matter of getting in there with the hose and the brush, and making sure that the valves are turned on the right way. It's just a matter of knowing, looking at a diagram and seeing like, okay, this should be open for the system to pump water to the end use. So a lot of these simple issues, but a sum of all these small issues can lead to a system simply not functioning. So this is a point I'd like to make, because working in a large institution is challenging. There are competing and conflicting interests at hand. For example, reducing water use versus the plants not dying. Having integrating more sustainable practices into the university versus working with a limited budget. So there are all sorts of differing goals, needs, and objectives of the administrative units in the University of Georgia. And because of that, sometimes they can be hard to reconcile. So this is, and something to take away is that there are no individual roles focused on the entirety of the rainwater harvesting system, i.e. there's no dedicated staff accountable for the rainwater harvesting system, and thus no ownership. And another point I'd like to make is the loss of continuous knowledge. So there have been multiple instances when I was talking with someone and they said, well, if you only knew Billy Bob, but he retired 5 years ago, he could tell you everything you wanted to know. And I've encountered that more than once. A matter of these people have deep knowledge and expertise with these systems, but that knowledge does not persist if it is not documented. So that is an important takeaway. Now, I'm going to end on this slide because I think this is the biggest takeaway for me, is that systems design thinking is critical. So this is both, I mean this in both in a technical and an administrative sense. In the technical sense, sometimes when these systems are not thought of as individual parts with functions that are interdependent on each other versus just, you know, a heap of, oh, this is the pump, this is the filter, and not this is the pump that supplies the water to this filter and it has to supply the water at this pressure in order for the water to pass appropriately through the filter, and think of these systems dependent on each other. Then you end up with a haphazard, motley approach to maintaining these systems. And in an administrative sense, individual administrative units are responsible at the moment only for individual components. This has also resulted in a patchwork approach to maintaining these systems. UJ's efforts were pioneering. There were very few precedents at the times. There were a few standards, there were a few codes. Some things worked and some things didn't work. There are a lot of good intentions, and this definitely can't be solved with one idea. These systems require a dedicated group, department, or individual for their success. That's definitely a takeaway that I like to drive home. And as stormwater management issues become more exacerbated, whether it's due to climate change or the growing amount of impervious surface, the university has the infrastructure in place to help solve them. These rainwater systems, ideas, they're in the ground, they're ready to be used again, and it still makes sense to conserve water. Most of the effort has already been done. So I like to think that I'm ending on a positive note, and I'm excited to see where rainwater harvesting at the university goes, and I'm excited to share a little bit of my story with you, and I hope that maybe there was a takeaway for y'all listening to this presentation. So thank you very much. So again, thank you for your time, and I believe now is the time for questions.